This program is brought to you by Stanford University. Please visit us at stanford.edu.
Let's proceed on with Poisson brackets. Phase space has a structure to it. It's not just a bunch of P's and Q's, but it's P's and Q's with a certain kind of structure. Spaces have structures. The structures are the things which are invariant under the various transformations that you might want to do. An example of the structure that can be on a space, if you know anything about curved spaces and differential geometry and so forth, the metric structure of metrical spaces, of Riemann spaces, are part of the structure of those spaces. They're characterized by a metric on the space, a distance formula between neighboring points. Poisson structures are different than metric structures. They're more abstract, and they were invented largely to describe the structure of phase space and its properties under transformations which change the coordinates. Now, the coordinates of a phase space are not just the Q's. The coordinates of a phase space are the Q's and the P's. And roughly speaking, the kind of question that you might ask is, what are the various transformations that you can do, for example, that mix up P's and Q's, that preserve the basic structure of classical mechanics? As I said, this is the kind of question, the kind of structural question, the kind of formal question that the French mathematicians were awfully damn good at. It turned out to be very important to the future of physics. It wasn't the French who figured out why it was important, it was the French who figured out how the basic structure, the French and Hamilton basically, who figured out what the structure of classical mechanics is. And it got more and more abstract. The most concrete version was, of course, Newton's version. The most abstract version, I don't know how abstract, you probably can get infinitely more abstract than anything I'm likely to teach you, but the most abstract end of it for our purposes is the Poisson formulation of classical mechanics based on the idea of Poisson brackets. What Poisson brackets do, or what they're useful for, is describing flows on phase space. One kind of flow on phase space is the motion of the phase space with time, or the motion of the points in phase space with time. How the actual points evolve with time under the influence of a particular Hamiltonian. That's one kind of flow on phase space. But there are other kinds of flows on phase space that you can imagine with possibly somewhat different purposes. For example, we can talk about symmetries. Now, we've talked about symmetries. The basic symmetry, the problem for me in explaining symmetries is not that it's hard to explain, it's that there aren't too many examples in classical mechanics that allow you a wide range of different situations to describe. The basic symmetries of most classical mechanical systems are rotations about various axes and translations. Special systems with particularly simple mathematics sometimes have some hidden symmetries that you might not have expected, but the basic symmetries are just those, the motions of space, translation, rotation. As you move on to more advanced physics, you discover more symmetries, different kinds of symmetries, symmetries among elementary particles and so forth, but those are not for us now. What do those symmetries have to do with flows? Flows in phase space? Well, let me begin with flows in just coordinate space, x space. We can think of a rotation. We can think of rotations in space as defining a kind of flow in the space. Just imagine going from here to here, rotating our coordinates in space by imagining an infinite number of intermediate configurations. And imagine in your head going from one configuration to another configuration of the axes of your space continuously. Or we don't have to imagine motion of the axes, we can actually imagine motion of a system where we rotate the whole system. We keep the axes fixed and rotate the whole room. That rotation might not have anything to do with the actual time dependence of the system. It simply allows us to describe mathematically what a rotation is. A rotation is something which is built up out of lots of little rotations, basically. And so we can think of the idea of a coordinate transformation, which rotates the coordinates of space, as a kind of flow. Likewise, the translation of space, the motion from one point, moving our coordinate axes, not rotating them, but translating them, we can also think of that as being built up, a given translation as being built up by a lot of little translations which define a flow. It's those flows in phase space, not just in coordinate space, but transformations which mix together or potentially could mix together both the P's and the Q's into a richer structure than just the transformations which mix up the coordinates. I use coordinates to mean Q's or X's. I use phase space to talk about the P's and the Q's. We can become interested, and we will become interested, in transformations which mix the P's and Q's. And so it's a richer family of transformations that we can imagine. And those flows, which move things around in phase space in various ways, are described by the method of Poisson brackets. So I try to make it a habit of not beginning in the middle, even though I may have covered something fairly completely in the previous lecture. So I like to go back over, even if it means I do it 2 or 3 times. Let's just review what we know about Poisson brackets. Okay? But let's be French mathematicians. Let's abstract. Rather than write down the concrete definition of a Poisson bracket, let's think about it from a more abstract collection of postulates or axioms about Poisson brackets. The Poisson brackets between what are Poisson brackets? What go into the Poisson brackets? A thing that I'll call A and a thing that I'll call B. Both A and B are imagined to be functions of the P's and Q's. So we can write Poisson bracket of A of P and Q with B of P and Q. First of all, has the abstract property that it's antisymmetric. Antisymmetric means that it changes sign if you interchange A and B. That's the first abstract property. Oops, minus sign, thank you. Most important thing, the minus sign. Right, so that's abstract property number 1. Abstract property number 2, I won't write down in detail unless you ask me to. It's the linearity. Oh, let me write it down. Supposing we have the Poisson bracket of some combination of A and B, let's say alpha A, alpha and beta are numbers, any numbers. Alpha A plus beta B, Poisson bracket with C, is just equal to alpha times the Poisson bracket of A with C plus beta times the Poisson bracket of B with C. So that's the property of linearity. This is antisymmetry. This is linearity. Then there's the product rule.
What kinds of things are the A's and the B's?
Capital A, what kind of what?
Things are they?
Functions. Functions of P's and Q's. P squared plus Q squared, sine of P, whatever.
It's real value,
Not necessarily.
but you can add.
There's no reason why in these formulas you can't take alpha and beta to be complex numbers.
But you can't add A's and B's, that's all I'm saying.
You can add oh yes, you can add A's and B's, absolutely. You can add A's and B's, just adding the functions. Yeah, you can certainly add A's and B's. They're just functions. In classical mechanics, there isn't much reason to be thinking about complex valued functions, but there's no reason that you can't. And sometimes you do. Sometimes you do. Sometimes it's useful. So they're just general functions of the coordinates and momenta. Remember, the coordinates, when I write down p's and q's, I don't just mean one p and one q. I mean n p's and n q's, where n is the number of coordinates of the system. Okay, so that's the linearity. Then there's the product rule. The Poisson bracket of A times B with C is equal to A times the Poisson bracket of B with C plus B no, A, thank you, B. Now I've written these formulas in a particular order here. I've left the A on the left here and the B on the right. There's no reason for that. These are just numbers. That is to say, they're functions whose values are just numbers. And it doesn't matter whether you multiply A times the Poisson bracket or the Poisson bracket times A. Mathematically speaking, these things all commute, which means you can multiply them in any order. I've written it in a form which won't mean anything to you now, but it will mean next quarter when we study quantum mechanics. In quantum mechanics, things don't commute, and I've written in a particular order which is still correct in quantum mechanics. But for our purposes now, A times the Poisson bracket of B and C is just nothing but the Poisson bracket of B and C times A. So it doesn't matter whether the B's come first or the Poisson brackets come first. It does matter the order that you write down the Poisson bracket itself. That order does matter because you have to change the sign if you want to change them. Yeah?
So these A's and B's have to be scalar functions.
Scalar has to do with their properties under rotation of space, and so.
I mean, it's not a vector.
They could be components of vectors. Vectors meaning.
I mean, if they were vectors or if they were matrices or something, it would matter. We're not talking about matrix multiplication, if that's what you mean. We're not talking about vector. We're talking about just numerical multiplication. Yeah. Let's not call them scalars. Let's call them numbers. Let's call them numbers. Numbers which simply mean that when you multiply two numbers, it doesn't matter which order you multiply them.
Yeah, mathematicians tend to just use the word scalar.
Oh, do they?
Yeah.
Well, physicists use the word scalar to represent the property of a system under rotation.
Functions of P and Q. The alpha and beta are scalars, but they're just functions because they depend on.
We're going to get into linguistic ambiguities here because it may be that mathematicians use the terminology different than physicists. Physicist means by a scalar something which doesn't transform under rotation of space. Okay? Mathematicians may use the word scalar to mean a number. Physicists often use the word C number, meaning a constant number. It doesn't matter whether it's constant or not. There's a whole terminology here that we'll get confused about. But the important thing is we're talking about multiplications which are commutative. But the Poisson bracket process itself is not commutative. A times B, A Poisson bracket with B is not B Poisson bracket with A. Okay, I think we know what we mean. Those are the basic abstract rules. And then there's some concrete rules. If the functions A and B are simply P's and Q's and nothing but P's and Q's, then we presume that there are some simple laws of Poisson brackets or simple rules for Poisson brackets for P's with Q's, P's with P's, and Q's with Q's. If we only had one P and one Q, then we could immediately write down that P with P, with now means Poisson bracket with. I get tired of saying take the Poisson bracket with. With simply means take the Poisson bracket. P with P can only be equal to 0. that follows from the anti-symmetry. P with P is equal to minus P with P from the top equation if we interchange the order. But if something is equal to its own negative, it's got to be equal to 0. Same is true with Q. What's that? Right. But that doesn't tell you what the Poisson bracket of P with Q is. Let's take Q with P. For that, we need to use the definition of the Poisson bracket, the definition in terms of derivatives, and then we just find out that it's equal to 1. Yeah, now if we put subscripts in, we can't be quite as confident that this is true for every I and j. Nevertheless, by the definition of Poisson brackets in terms of derivatives, remember that every Poisson bracket has in it derivatives with respect to P and derivatives with respect to Q. Well, you can't differentiate a P with respect to Q. You get 0. So anytime you take a Poisson bracket of a P with a P, you must get 0. A Q with a Q, you must get 0. But a Q with a P, you get 1 or 0, depending on whether I is equal to j. Delta ij. Delta ij is the Kronecker symbol. Kronecker. I don't know if I spelled that right or not.
No.
No C here?
No.
I don't know. Yeah, it's either 0 or 1 depending on whether I is equal to j or not. Namely, it's equal to 1 if I is equal to j and 0 otherwise. That's the Kronecker delta symbol. And that's the, these are the Poisson bracket relations for P and Q. Now, it's easy to prove that if you take, well, in fact, you can prove almost everything about Poisson brackets just from these relationships. But if you also allow yourself to use the definition of the Poisson bracket, which can be derived, incidentally, from these relations. But if you use that, you can also immediately prove that the Poisson bracket of any function of the Q's, not the P's, with any other function of the Q's, in other words, if both functions only have Q in them, that's automatically 0. Why? Because again, every Poisson bracket will have derivatives with respect to P and derivatives with respect to Q in its definition. So at least, so it will turn out to be 0 if there's nothing to differentiate with respect to P, so to speak. All right? So this will be 0. Likewise, any function of P with any other function of P will also be equal to 0. It's only when you take Poisson brackets between functions of P and with functions in which at least one of them has both P and Q in it. No, that's not right. What do we have to say? Something on one side has to mismatch something on the other side. There's got to be a P on one side and a Q on the other side to get anything non-zero. Okay. So that's a collection of rules. There are more rules, but they all follow from these. There's no independent rules. For example, supposing we take the Poisson bracket of any function of Q with P. Poisson bracket of any function of Q with P. What is that equal to? Well, I'll tell you right now what it's equal to, and then we'll try to prove it. That is equal to the derivative of f with respect to Q. So taking a Poisson bracket with P is the same as differentiating with respect to Q. We can see that in a number of ways. One way of seeing it is just use the definition, but another way of seeing it is here. We can prove it by mathematical induction. Let's prove it for all polynomials f of q. If we prove something like this for every conceivable polynomial, it will be true for every function. Every function can be arbitrarily well approximated by a sufficiently complicated polynomial. The linearity would tell us we need to only prove it for monomials. So let's prove it for some monomials. Let's take 1. Let's take f of q equals 1. What does this equation say for f of q equals 1? It says the Poisson bracket of 1. 1 is a function. It's a perfectly good function. It doesn't vary, but it is a function. 1 with p must be equal to the derivative of 1 with respect to q. What is the derivative of 1 with respect to q? 0. Now, how do I prove this? I'll tell you how I can prove it.
One is just as good as f of p as an f of q. So
Yeah.
by the bond relation, just
Yeah, but I didn't prove these. But let me give you a simple proof of this one. The simple proof of this one is to use the product formula. 1 squared with p is equal to 1 with 1p plus 1p with 1, which is equal to twice Poisson bracket of 1 with p. But 1 squared is just 1. So this says that the Poisson bracket of 1 with p is twice the Poisson bracket of 1 with p. That proves it's 0. Okay, so indeed, the first one is right. Let's go to the next monomial, q with p. That's the next more complicated monomial for f. Q with p should be equal to the derivative of q with respect to q, which is just equal to 1. But that's certainly true. That is the defining property of q with p. Let's just go one more, q squared with p. Q squared with p, for that we use the product formula again, and that gives us q with qp plus qp with q. Poisson bracket of q with p is just 1, so this just gives us 2q. And that happens to be the derivative of q squared with respect to q. All right, so by a process, of course, we use mathematical induction to prove it for q to the nth. Once you proved it for q to the nth, then you use linearity to prove it for every polynomial. And then to go from polynomials to arbitrary differentiable smooth functions, you can use the fact that any smooth function can be approximated arbitrarily well by a polynomial. So, in fact, we see that Poisson bracketing with p is simply another way to differentiate. Likewise, differentiating with respect to p is the same as taking the Poisson bracket with q. Notice there's a slight difference in the order of Poisson brackets here. To differentiate with respect to q, you take the Poisson bracket with p on the right-hand side. To differentiate with respect to p, you put the q first. All right, so that's another property. Yeah.
So are you assuming that Poisson brackets are continuous in each variable?
Yeah. Assuming everything is continuous, functions, every function is continuous, differentiable, multiply differentiable. And we're assuming that, yeah. All right, so we have our, one could say we have an algebra of Poisson brackets that characterize the relationships between p's and q's in the phase space. Now we add to that another postulate about the time evolution of a system, and that postulate again can be derived, it can be completely derived from Hamilton's equations. We've derived it at least twice as I remember, but let's just write it down. It can be just added to these postulates as one more postulate, and it is that the time derivative, A dot, of any function of p and q, let's just remember what that means. We have the phase space, which is coordinatized by p's and q's. We have points of phase space moving through the phase space under the equations of motion of a system. And as they move through the phase space, the value of A of P and Q will change along the orbit of the phase point. Right? That's what A dot means, the rate of change of A of P and Q because you're moving along the orbit in phase space. That time derivative is the Poisson bracket of A with H. This basically sets the pattern that a flow applied to a function, we have a function on the phase space, and we apply the flow to it, we apply the flow to it, that causes the function to change as we move along the flow. That flow is characterized as a Poisson bracket with something. That something happens to be the Hamiltonian if we're talking about the genuine flow with time. Okay? In other words, the real flow of the system as time evolves. But we may just be interested in some mathematical flow that has nothing to do with the time evolution, but just has to do with the fact, for example, that we're studying some symmetry, which might correspond to a change of coordinates through a sequence of intermediate coordinate configurations. Yeah.
From an abstract standpoint, without bringing in Hamilton, does this basically assume that P's and Q's are functions of time, basically? If we didn't want to think about
Yeah. But of course we could apply, yes, but we could just apply this to the P's and Q's and see that they're functions of time just by saying that P dot is Poisson bracket of P with H. And then if we know H, if we know what H is as a function of P and Q, let's, for example, let's just see what happens if our Hamiltonian happens to be P squared over 2m. And we apply this to P dot. It tells us that P dot, time derivative of P, is the Poisson bracket of P with P squared over 2m. Well, that's 0 because of a formula which I think I have erased, which says that the Poisson bracket of any function of P with any other function of P is 0. Okay? So that's 0. That tells us momentum conservation. On the other hand, Q dot is Q with P. Now we use the product formula. We use the product formula. We have P squared here and Q here. The product formula can be used to tell us that this is just P over M. We have P squared over 2m. That gives us a P with a Q is 1. Well, you know how to do this. Just gives us a P over m without ever using anything other than the algebra of these functions, the algebra of these Poisson brackets. We can conclude that the Poisson bracket of Q with P squared over 2m is P over m. And that tells us that Q dot is P over m. And that, of course, is the velocity as a function of momentum for a non-relativistic particle with Hamiltonian P squared over 2m. All right, so without knowing Hamilton's equations, we could derive the equations, Hamilton's equations, from the algebra of these Poisson brackets. Okay, now let's come to a wider class of transformations. Yes?
Just a little tangent on that. You said non-relativism. Does this actually hold up on the relativity?
Yep. But it's a little more complicated. Yes, it does. These basic formulas hold for every physical system that I know of. I don't know of any physical system where these basic formulas don't hold, including general relativity, including quantum field theory. Well, in the appropriate form in quantum mechanics, the appropriate form in quantum mechanics they hold. But for all classical systems, these formulas absolutely hold. Quantum field, field theory, electromagnetism, everything. Okay. Now let's move on to symmetries. What are symmetries? Symmetries are transformations. Transformations of a system which don't change the dynamics. Now, in the cases we've studied up till now, symmetries were typically of the form changes of the variables Q without mixing in the P's. For example, rotations of space mix up the x's and the y's. They don't mix in the momenta with the x's and y's. Could there be more interesting symmetries of nature which do mix the p's and q's? And if they do, what are the rules and what are the laws which allow you to mix up p's and q's and preserve the structure of classical mechanics? That's the question. What are the allowable transformations that don't screw up mechanics so badly that it becomes unrecognizable? Recognizable means that it has the Poisson form. Right, so that's a question we want to ask. What are the allowable transformations on phase space? Allowable transformations mean they don't ruin this Poisson structure that we've written down. If you were just to take a bunch of P's and Q's which satisfy this algebra of Poisson brackets and make arbitrary transformations, let's do it this way. Let's suppose we have a single P and a single Q. Now, let me make a transformation. I'm going to make a new transformation to new P's and Q's, capital P, which is going to be twice little p, and capital Q, which is twice little q. Does this preserve the Poisson bracket structure? It does not. Let me show you why. Let's calculate the Poisson bracket of big P with big Q. Well, that's easy. I don't even have to do any work here. I just know that this is the Poisson bracket of twice little p with twice little q. What's that? 4. It's the wrong answer. It does not preserve the form of the Poisson bracket relations. Let me try something else. Instead of big P equals twice little p, let's take it to be 1/2 little p. Now what happens? What's the Poisson bracket of big P with big Q? 1. This formula has preserved the structure of Poisson brackets. If I do this transformation on the P's and Q's, it's not necessarily a symmetry of a physical system, but it is another set of coordinates which has exactly the same Poisson bracket relations as the original P's and Q's. It's kind of interesting. What I've done to the phase space is I have squeezed it in one direction by a factor of 2 and stretched it in the other direction by a factor of 2. And that has preserved the structure of the Poisson bracket relations. Stretching both directions by a factor of 2 did not preserve the relations. How about the following? Supposing let's try another example. Let's take.
Is that an intuitive result? I mean, it's
It's basically conservation of area. Yeah. But it's conservation, it's a little more complicated. Once you leave the domain of just one P and one Q, it's more complicated. But for one P and one Q, the transformations that we're talking about are the ones that preserve areas. For more P's and more Q's, it's more complicated. But let's just do one or two more examples. Let's take big P is, let's rotate P into Q. Rotate P into Q. In other words, we have the PQ axes and we rotate. Let's take big P equals cosine theta little p plus sine theta little q. And let's take big Q equal minus sine of theta little p plus cosine theta little q. This is the form of a rotation in phase space. It's a rotation in phase space where you've rotated the axes. From what I just told you about areas, it's quite clear that this also should preserve the structure of Poisson brackets. Let's check it. Let's calculate the Poisson bracket of big P with big Q. Do I have to check the Poisson bracket of big P with big P? Big P with big P. This is linguistically the hardest lecture for me. Do I have to check the Poisson bracket of big P with too many B's and P's? Big P with big P. What's that?
By linearity, it all works. It all just combines.
Well, let's just say big P with big P. Anti-symmetry tells me it's 0. Big P with big P has to be the same as big P with big P in the opposite order. That tells me it's 0. Anti-symmetry tells me big P with big P is 0. It tells me big Q with big Q is 0. It's only big P with big Q that I got to watch out for. Okay, so let's just do it. So that's going to be, big Q with big P equals sine theta, let's begin with Q's. All right. Cosine theta Q plus sine theta P, that's this one here. There's one of them minus, one of them is minus, right? This one is minus. And then the other one is cosine theta P plus sine theta Q. All right, the only combinations which give me anything are a Q with a P and a P with a Q. All right, let's first take the Q with the P over here. That's going to have cosine squared theta in front of it. Cosine squared theta, Poisson bracket of Q with P. Poisson bracket of Q with P is 1. And then we're going to have minus sine squared theta. That's coming from here. But what's the Poisson bracket of P with Q? Minus 1. So that corrects this sign here and makes it plus sine squared and gives us a 1 again. All right, so the rotation of coordinates preserve the Poisson bracket structure. The stretching of one coordinate and the squeezing of the other coordinate by the same factor, it didn't have to be 2 incidentally, that will preserve the Poisson bracket structure. On the other hand, other kinds of transformations will not preserve it, in particular those that don't preserve the area. So there are those which do and those which don't. Those transformations which preserve the entire class of them, and they can be much more complicated than this, in general, for arbitrary numbers of P's and Q's, the transformations which preserve the Poisson bracket structure are called canonical transformations. Canonical. Canonical transformations are those which keep intact the relations between the Poisson bracket relations between P's and Q's.
If they keep the relation between p's and q's, then they will keep all the Poisson bracket relations between p squared, q squared, p whatever you have.
So
What-
also leaves the equations of motions.
What's that?
The equation of motion should be unchanged also.
Yeah, but you have to remember that when you change that the Hamiltonian has to be expressed in terms of the new variables. Yes, that's correct.
So when you generate the Poisson
That's right.
bracket, that would give you the equation of motion.
That's right.
These are really examples of gauge transformations.
No, these are not gauge transformations. No, these are canonical transformations. They're not gauge transformations. They're not redundancies of a description. They're just changes of a description to new coordinates.
The gauge transformations, you're adding something on to the existing coordinates of fields, but in this case, you're actually transforming the coordinates themselves.
Well, those are not called gauge transformations. Gauge transformations have a definite meaning.
At this system, how do you know that P and Q are canonical?
Now, the point is, if you start with canonical p's and q's, and you do canonical transformations on them, they stay canonical. Now, that's a tautology. But to make it not a tautology, what do you mean by canonical? You mean these Poisson bracket relations. These are the canonical Poisson bracket relations. If after transformation, all of the Poisson bracket relations are kept intact, then it's called a canonical transformation. Okay.
I have a general question about, must it preserve the Poisson bracket to be a canonical transformation? As opposed to, I guess, well, let's say if you have any two sets of p's and, small p's and small q's and big p's and big q's.
Well, big P's and big Q's being functions of the small p's and small q's.
Okay.
They're changes of coordinates is what they are. They're changes of p, q
You're
coordinates.
saying you might have two different sets of coordinates of different systems.
No. We're talking about different coordinates for the same system. That's what we're talking about. Different coordinates for the same system. And by coordinates, I now mean coordinates on phase space. So we're talking about different representations of the same system by different choices of axes or different choices of coordinates on the same phase space.
So you can't go from arbitrarily one phase space to any other
No.
phase space.
We're talking about the same system.
All right, good.
Yeah, these are changes of description rather than changes of system. Okay, changes of description of a given system. Right, we must keep that in mind. It doesn't mean anything, for example, to change the coordinates of, from a harmonic oscillator to a system of 10 to the 23rd molecules. It doesn't mean anything.
You won't necessarily have a canonical transformation that transforms one totally different system to another.
It doesn't mean anything. I mean, if it does mean something, we have to make up a definition for what it means. Here, we're talking about P's and Q's, which are really functions of the original P's and Q's, which means they're just redescriptions of the same system. Yeah.
But aren't they just characterized by dimensionality? I mean, if n is 5, there's a whole set of canonical transformations for 5 p's and 5 q's.
Yeah. The phase space of n degrees of freedom are all isomorphic to each other. But still, nevertheless, when you're talking about canonical transformations, you're talking about the changes of description of a given system. Yeah, but the different phase spaces, all with the same number of degrees of freedom, are isomorphic to each other. That's correct.
Transformations are, if it works on one, it works on another.
Yeah? Yeah? But still, you don't transform between systems. Right. All right, now we want to come to what is the heart of the discussion, the subject of symmetries itself.
Is there any way of expressing sort of necessary and sufficient conditions for something to be a canonical transformation, other than the way you put it, or are you going to get to that?
This is the necessary and sufficient condition, that the P's and Q's preserve their Poisson bracket structure. That is the necessary. Now you're asking if you give me a certain, well, what are you asking?
I guess is there another way of expressing it in some way other than, that's of some general interest?
Yeah. Yes. Yes, there is another way of expressing it that is of great general interest, but is also not completely general. We tend to build transformations, not all of them, but we tend to build transformations out of infinitesimal transformations, out of small steps. Okay? If we're talking about an infinitesimal transformation, I'll explain exactly what I mean by an infinitesimal transformation in a moment, but I think you know what I mean, though. Yeah. Yeah. If we're talking about infinitesimal transformations, then yes, there is a way to describe them, a unique, special way to describe them, which we're about to come to now. So if we can build up the transformations out of infinitesimal transformations, and what is an infinitesimal transformation? It means well, let's just write down what it means. It means Q is almost exactly equal to little q, but with a very small deviation. And that small deviation we'll just call delta sub q, delta of q. And this, of course, is a function of the q's and the p's. It just means the deviation from a trivial transformation, big Q equals little q, is infinitesimal. In practice, what it means is in their formulas, we will drop things proportional to quadratic and higher powers of the deltas. It means that small quantities mean quantities which are so small that we can drop higher powers in them. That's what we'll always mean by an infinitesimal operation, that we can drop higher powers. Now, we can always build transformations out of sequences of little transformations for each one of which we can drop higher powers, but then we have to combine them together, and sometimes that makes something more complicated. But we can test out very easily what are the rules for infinitesimal canonical transformations. I won't bother writing down that it's a function of P and Q. All right. Let's just remember that the deltas are themselves functions. They're functions, but they're small, such that we can ignore higher powers of them. All right, let's first write down the condition that this be a canonical transformation. Incidentally, of course, there are some indices here. I'll suppress the indices up until the last step. Let's write down the condition that this be a canonical transformation. Right? It just says that, let's just do it as if it was just one P and one Q. And we can fill in the gaps later. Okay. Poisson bracket of big P with big Q. That's the interesting one here. Okay. Big P with big Q. That's just going to be the Poisson bracket of little q with little p. We'll stick in the i's later. Plus the Poisson bracket of delta q with little p. Plus the Poisson bracket of q with delta p. I've just stuck in for big Q, Q plus delta Q, for big P, P plus delta P, and then used linearity to expand it out. I've left out one term. I've left out the Poisson bracket of delta Q with delta P, but that's already quadratic in small quantities. Quadratic in small quantities are too small to be significant. So this is our formula. Now, what do we want to be true? We want this to be equal to this. So a necessary and sufficient condition, then, is that delta Q with P should be equal to minus Q with delta P. Let me show you how to satisfy that. This actually is necessary and sufficient, but it's not hard to show that it's necessary and sufficient, but let me just show you the construction. What do? We write that delta Q is equal to some small number. The epsilon is just a small number in the problem. Delta Q, delta P are all proportional to the same small number. I introduced explicitly the small number so that I'll know, so I keep track of it, times the Poisson bracket of Q with something. With what? With an object that's called the generator of the canonical transformation, G of P and Q. And delta P is equal to epsilon times P with G. Another way to say it is that every infinitesimal canonical transformation is characterized by a function, G of P and Q, which itself defines a flow.
Is it the same or reversed in order?
Same order. Same order. All right. This is a kind of flow. A coordinate transformation, in particular an infinitesimal coordinate transformation, is a kind of flow on the phase space. You take every point and you shift it a little bit. You take every point and you shift it a little bit. That's a flow on the phase space. And flows on the phase space are characterized by things called generators. Generators are functions of P and Q, and they characterize how the flow takes place. Let me prove now the theorem. I'm going to prove the theorem that says that if delta Q and delta P are obtained by Poisson brackets with a generator, then this will always be true. It goes the other way also. All right, this is not hard to prove. First of all, what is the Poisson bracket of Q with G of P and Q? Remember, taking a Poisson bracket with Q is the same as differentiating with respect to P. What is this? This is dq by dq, dg by dp, minus, this is just epsilon dg by dp. Just using the definition of Poisson bracket now. dq by dq, dg by dp, that just gives you dg by dp. And then dq by dp, that's 0. What about this one? This one is equal to minus epsilon dg by dq. So now we have specific formulas for delta p and delta q. Here they are. Let's plug them into this formula over here. What's delta q? Delta q is epsilon dg by dp. Epsilon Poisson bracket of dg by dp with p, and that should equal minus Poisson bracket of q with delta p. What's delta p again? Delta p is minus dg by dq, right? Epsilon. All right, the minus signs cancel themselves out, I hope. And what is the Poisson bracket with P? It just differentiates with respect to Q. So this is just the second derivative of G with respect to P and Q. What's Poisson bracket with Q? Derivative with respect to P. This is identically, the left side and the right side are identically equal to each other. Okay. They're identically equal to each other, each one being the second derivative of G with respect to P and Q. Okay. So, okay, so here's what we find. We find that flows which are generated by Poisson bracketing with respect to a generator always define canonical transformations. A special case of this is the Hamiltonian flow. Let's just look at this equation here. What does it say? Supposing we were talking about the time motion of a system. The time motion of a system is Q dot equals Poisson bracket of Q with H. Well, if I write that Q dot is delta Q by delta T, and I just think of delta T as a small epsilon, let's put epsilon here. In other words, I change the time interval by amount epsilon, then the Hamiltonian flow is exactly the same as the sort of thing I've written here. Hamiltonian evolution of a system is a canonical transformation. In other words, the coordinate transformations of P's and Q's, which are generated by the actual flow of the system, is itself a special case of a canonical transformation. Furthermore, all canonical transformations can be generated by picking some generator, as if it were the Hamiltonian, imagining in our mind a Hamiltonian which caused a flow which took the points from one to another. That defines the most general class of canonical transformations. Now, yeah, the most general, I think I'm saying something a little too strong. I'm not sure, maybe I'm not. Every canonical transformation that I know, now I know I'm saying something correct. Every canonical transformation that I know of, I think it's true, can be generated from infinitesimal canonical transformations. If it can be generated from an infinitesimal canonical transformation, then it's got a generator G of P and Q, which allows it to be constructed in this way. So, if you want a small canonical transformation, which just displaces the points a little bit, you just take Poisson brackets of the variables you're interested in with the generator, and that gives you the changes in the phase space coordinates. That's the basic idea, that all motions on the phase space, whether they have to do with the actual time evolution or whether they just have to do with coordinate transformations moving points around, are of the form of canonical transformations generated by generators, the Hamiltonian being a special case. Yeah?
Are there any restrictions on what the Hamiltonian can be? It looks like G is just a Hamiltonian for another system.
Yeah. It is. It's just, it could be the Hamiltonian for another system. And the Hamiltonian could just be some arbitrary flow. That's right. What the Hamiltonian is, of course, is really determined by the physics of a system, experiment, and all that kind of thing. But the mathematics cannot tell you whether G is the Hamiltonian or H is the Hamiltonian. You do an experiment to find out. Okay, now we can discuss if the transformations which we are allowed to do, which preserve the structure of mechanics, are canonical. Then what is the subclass of those? For a given system with a given Hamiltonian, what is the subclass that are called symmetries? Symmetries are the canonical transformations which don't change the Hamiltonian. Just like in the case of Lagrangians, we said that the symmetries were the coordinate transformations which didn't change the Lagrangian. Now the more general idea becomes
coordinate transformations in phase space, which are canonical and which don't change the energy, those are the symmetries of a mechanical system. We can actually say that in a somewhat geometric way. Here's our phase space. Oh, incidentally, I didn't keep track of the little indices I. You can go home and do the derivation over again, keeping track of all the indices I and j, and see that the construction still works. It's more or less obvious. Okay. But let's imagine here's our phase space, multi-dimensional phase space. Now, the Hamiltonian corresponds to some flow. And it's also a canonical transformation. The infinitesimal small time flow from one point to another is the canonical is generated by the Hamiltonian, and the full transformation over a period of time is canonical. Now let's imagine there's some other quantity, a generator G, that generates another flow. It's not to be thought of as the time evolution of a system. It's just another flow on the phase space. Just another motion on the phase space, which moves points through the phase space in some other way. In general, you can see from this picture that the new flow, the green flow, will change the value of the energy along the flow. But supposing it's true that the green flow, G, and the black flow, H, the Hamiltonian of the system, are in just such a way that the flow along the G direction doesn't change the energy, causes the energy not to change at all. In other words, flows the system along surfaces of constant energy. Then it's called a symmetry. It's a symmetry, G is a symmetry, if the flow created by G doesn't change the energy. What's the condition for that? This is easy. Right, right. Geometrically the condition, but in a multi-dimensional space it's not so obvious. All right. Here's how Q and P change under the flow. Let's take a general function of P and Q. Let's take a general function of P and Q and see how it changes along this flow. I'm going to call the function A again. Let's call it A. How does A change along the flow? Well, it changes dA by dP times delta P plus dA by dQ delta Q. But what is delta P and delta Q? Here we have them. They're proportional to GP, but dG by dP and dG by dQ. So this is, let's see, delta P is dG by dQ. dG by dP. In other words, not too surprisingly, the change in any function of A is just proportional. There's an epsilon in here, isn't there? Is just epsilon times the Poisson bracket of A with G. This is exactly the same formula we use for time derivatives of things when G was the Hamiltonian. The change of functions along the Hamiltonian flow is just a Poisson bracket with the Hamiltonian. The change of an arbitrary function along any flow is just a Poisson bracket with the generator of the flow. That's what these generators do. Poisson brackets with the generators create the flow, and they give you the derivatives or the way the functions change along the flow. All right, so then, what does it say that the energy does not change along the flow G? It says that the Poisson bracket of H
with G is equal to 0. It says that H does not change along the flow G. Right? If I were to just plug in here for A, H, everywheres, this would just be the Poisson bracket of H with G. So this is the condition that the energy doesn't change along the symmetry flow G. But now we can read this the other way also. This also tells us that G with H is equal to 0. H with G and G with H are just the negative of each other. And what does this equation say? This says that the time derivative of G vanishes. Right? Remember, the other equation was that A with H equals A dot. The same equation which says that H doesn't vary along the flow G says that G doesn't vary along the flow H. But what does this equation say? It says that A is conserved. Right? It says that A is conserved. So if you have a Hamiltonian and you have a generator G, a quantity G, which has the property that the flows created by G don't change the energy, then the flows created by the energy, that's the time dependence of the system, don't change G. This is kind of the reciprocal relation. It's an interesting reciprocal relationship. If you have two quantities, H and G, and you say H is the Hamiltonian which generates the time dependence, and G doesn't change the Hamiltonian, then if you switch the system and you said G was the Hamiltonian, and H was just some arbitrary thing, I think you get the point. I'm going to use too many words to say it. There's a parallel relationship between quantities which are conserved and the energy of a system. Parallel, symmetrical relationship between them. I think this would be a good point to stop. This is a very, very highly abstract business. And it does have to do with the intrinsic structure of classical mechanics. But as I said to you time and again, the place where the real glory of this comes forth is in quantum mechanics. It's very abstract in classical mechanics. It's extremely concrete in quantum mechanics. Much easier to understand in quantum mechanics.
What could be an example
Of what?
in quantum mechanics?
Angular momentum and energy. H could be, let's see, H could be the energy of a system. It could be p squared over 2m plus, I don't know, function of x squared plus y squared, let's say. That could be H. G could be the angular momentum. Angular momentum is xpy minus ypx. If you calculate the Poisson bracket between this and this, you'll find that it's 0, corresponding to, let's do that. Oh, yeah, that's going to be complicated. Let's do it for a free particle. It's going to be a little too complicated to do in general. Yeah, let's do it for a free particle. Okay, so let's take p squared over 2m, and that means px squared plus py squared. Do you mind if I set m equal to 1? No. Px squared over 2 plus py squared over 2. That's the Hamiltonian. G is the angular momentum. The expression for the, this is 2 dimensions, just for simplicity, 2 dimensions. G is the angular momentum. That's xpy minus ypx. Okay, now we want to start calculating Poisson brackets between G and H. This is not too bad. Remember, all p's.
It's all P's.
No, this isn't p's.
Oh, yes, so.
Right.
I didn't see the Q.
Yep. X's and Y's are Q's. Good. All right. It wouldn't be true if I just took xpy or ypx, but it's a combination xpy minus y. Okay, so let's do it. Poisson bracket of G with H. Okay, so what is that? It's going to have xpy with px, and it's going to have xpy with py. How about, let's do xpy with py first of all. Do I get anything from that? The Poisson bracket of an x with a py is 0. Remember, the only non-zero Poisson brackets that you begin with are x with px and y with py. When I start calculating xpy with py, I'm not going to get anything. Py Poisson bracket with py is 0, x with py is 0. So there's nothing on this side which has a non-zero Poisson bracket with anything over here. The only non-zero Poisson brackets are x with px and y with py. Okay, so let's begin with x with px. This is going to be then Poisson bracket of xpy with px squared over 2. And then the other term will be minus ypx with py squared over 2 with py squared over 2. Okay, how about xpy with px squared over 2? Well, we use the product formula here. We take out one term is just py with xpx squared over 2. Then there's another term where the x comes out and py gets Poissoned with px. But what's Poisson of py with px? 0. So this is the only term coming from the first bracket. Py times x with px squared. What's x with px squared? Remember what Poisson bracketing with a q does. It differentiates. So x with px squared gives what? Just px. This whole thing is just py px. It's just py px. What about this one? We'll get a px on the outside, and we'll get y with py squared, which will be py, which will just be minus py px. So this is an example of two generators which have 0. I keep wanting to use the word commute. In quantum mechanics, it would be commute. But let's not use that terminology. This is an example of two quantities, two generators, which have vanishing Poisson bracket between them. The implication is the following. If the Hamiltonian is px squared plus py squared, then the angular momentum is conserved. If we invented a new system where the Hamiltonian happens to be this thing, crazy Hamiltonian, but let's do it anyway. A new system where the Hamiltonian is this thing, then this object would be conserved. The Poisson bracket between them is 0, so whichever one is the Hamiltonian, the other one is conserved. Okay. And again, the idea that the Hamiltonian doesn't change under a transformation, that is the basic idea of a symmetry. That a symmetry is an operation which doesn't change the energy. Okay. But we see here there's a rich structure to the whole thing, a much richer structure than you might have expected. Okay, any questions about this? And then I want to move on to, I want to move back and review what we said the first time. Yeah.
You got a system where G is the Hamiltonian.
Where it said, yeah, oh.
What does that mean?
Let's see what it means. Let's see what it means. To see what it means, it simply means let's find out the equations of motion that go with it and ask how a particle would move under the influence of that Hamiltonian. I don't know, let's see. I never worked it out. Here's a Hamiltonian, new system. Hamiltonian is xpy minus ypx. Let's work out Hamilton's equations. Hamilton's equations say x dot is equal to the Poisson bracket of x with h. What's the Poisson bracket of x with h? Can anybody read this off? Where does it come from? Which term? The only term in H which can contribute to a Poisson bracket with x is a term that has px in it. So this looks like it's going to be minus y. X dot equals minus y. And what about y dot? Y dot is equal to x. Anybody have any idea what kind of motion this is? Circle, circular motion. It just describes something going in a circle.
So you're saying now H is equal to what was the generator?
Yeah, I've interchanged now. So let's make up a new system where the Hamiltonian just happens to be xpy minus ypx. And what do I get? I get a system which just moves in a circle counterclockwise direction, like so. So if we had some mechanical system which could only move in a circle, we would describe it by this Hamiltonian, but then we would find that px squared plus py squared was conserved. And in fact, that would be true.
You've gone through these with just a P and a Q, and what I want to confirm is my sense is you're always talking about the same index,
Well,
and that for each index,
yeah.
the transformation could be different?
For each index, the transformation could be different. Yes. Yeah, but it's more complicated than that. The transformation, no, there's one, okay. It's not that there's a transformation for each index. There's a set of transformations. Well, there is a transformation for each index. I take that back. Qi is a function not just of Qi and Pi, but of all the Q's and P's. Okay? So there's a transformation for each index, but each transformation in general involves all the Q's and P's. Yeah. Right. Yeah.
What's the condition for getting P if you know Q?
Say it again.
What's the condition for getting P if you know Q? I remember what it was when we were back in Lagrangian, but in this form, what is the momentum that's canonical with a Q? How do you define?
Oh, how do you get the momentum in terms of Q's? I think for this system, Py is actually equal to x, and Px is equal to minus y. Let's see, can we see why that is?
I'm talking about the general definition. I remember
You mean, how do we find the P's in terms of the velocities?
yeah, if you have a Q, how do you know the formula for the P that goes with it? It's not always.
I think the question you're asking is, how do you know the P's in terms of the velocities?
Okay, yeah.
I think that's the only question I can think of that you could ask.
It's not always MV.
It's not always MV, no, but you go to Hamilton's equations. You go to Hamilton's equations, and let's do it for an ordinary case and see how it works for an ordinary case. We could have H is equal to P squared plus some U of X, okay? Let's just do it for them. let's just do it for the good old familiar simple particle, and we'll see the pattern. All right, so we just go to Hamilton's equations. Hamilton's equations are x dot equals Poisson bracket of x with h, and that's just going to give us p over m. That's it. That's it. That tells us p in terms of x dot. The other equation is the equation that p dot is equal to p with h, and that gives us du by dx. And that's, of course, F equals ma. Force is equal to mass times acceleration. So one of the Hamilton equations, typically, the usual situation is one of the Hamilton equations tells you the relation between the p's and the x dots, and the other is, like Newton's equations, involves the acceleration. Yeah.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.